These are the answers to the AP Chemistry packet that covers topics 5.4 to 5.11. On this slide, you can see Unit 5 at a glance. Unit 5 is entitled Kinetics. In this video, we will take a look at topic 5.4, Elementary Reactions, topic 5.5, Collision Model, topic 5.6, Reaction Energy Profile, topic 5.7, Introduction to Reaction Mechanisms, topic 5.8, Reaction Mechanism and Rate Law, topic 5.9, Pre-equilibrium Approximation, topic 5.10, Multistep Reaction Energy Profile, and topic 5.11, Catalysis. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. The content in topics 5.4 and 5.7 are closely related to each other, so I have combined these two topics together in this section of the packet. Topic 5.4, Elementary Reactions. Here are some essential knowledge statements from the AP Chemistry course and exam description. The rate law of an elementary reaction can be inferred from the stoichiometry of the particles participating in a collision. Elementary reactions involving the simultaneous collision of 3 or more particles are rare. Topic 5.7, Introduction to Reaction Mechanisms. Here are some essential knowledge statements from the AP Chemistry CED. A reaction mechanism consists of a series of elementary reactions or steps that occur in sequence. The components may include reactants, intermediates, products, and catalysts. The elementary steps, when combined, should align with the overall balanced equation of a chemical reaction. A reaction intermediate is produced by some elementary steps and consumed by others, such that it is present only while a reaction is occurring. Experimental detection of a reaction intermediate is a common way to build evidence in support of one reaction mechanism over an alternative mechanism. In topic 5.2, you were given the following advice about determining the order of a reactant. The order must be determined from experimental data. You cannot assume that the order of a reactant is simply its coefficient in the overall chemical equation. This is because the overall equation does not tell us exactly how the reactant particles collide with each other in order for bonds to break and/or form. So again, for example, you have an overall balanced chemical equation in which 2 moles of nitrogen monoxide react with 2 moles of hydrogen to produce the products nitrogen gas and water. So the rate law indicates that it's second order with respect to nitrogen monoxide and first order with respect to hydrogen. So notice that the coefficient of 2 in the overall balanced chemical equation does not match the order with respect to hydrogen in the rate law. Now, there is a difference between an overall chemical equation and what is known as an elementary reaction or an elementary step. So if you are asked to write the rate law for an elementary step in a mechanism, now you can say that the order with respect to a certain reactant is equal to its coefficient in the elementary step. So the difference is that an elementary step represents a collision event between reactant particles. And so that is very closely related to the order of that particular chemical in the rate law. So here's an example. On this slide, we can see a collision between 2 molecules of NO2. And as the molecules collide, a new bond is formed and a bond is broken. So if this were an elementary step of a mechanism, it would be second order with respect to NO2 because there are 2 molecules of NO2 colliding with each other. Here we have another example of a collision. We have a molecule of CO colliding with a molecule of NO3. A new bond is formed and a bond is broken. If this were an elementary step of a mechanism, it would be first order with respect to NO3 and first order with respect to CO because there is one molecule of NO3 colliding with one molecule of CO. All right, let's take a look at number 1 in your packet. The chemical equation shown above, which involves nitrogen dioxide, NO2, reacting with carbon monoxide, CO, to produce nitrogen monoxide, NO, and carbon dioxide, CO2, this equation provides information about the reactants and the products. However, it does not provide details about how this chemical reaction takes place at the particle level. So we have a reaction mechanism, and this has been proposed for the reaction between NO2 and CO. The proposed mechanism consists of 2 elementary steps. Part A, write the rate law for elementary step number 1. So since in step number 1 there are 2 reactant molecules of NO2 colliding with each other, then this elementary step would be second order with respect to NO2. So the rate law would be rate equals K times the concentration of NO2 squared. Again, second order with respect to NO2. Now for the rate law for elementary step number 2, we see that there's one molecule of NO3 colliding with one molecule of CO. Therefore, this is first order with respect to NO3 and first order with respect to CO. So the rate law for that particular step would be rate equals K times the concentration of NO3 times the concentration of CO. Again, these are to the first power, first order, one molecule of each. In part C, the definition of an intermediate is a substance that is formed as a product in an earlier step of a mechanism and then consumed as a reactant in a later step of the mechanism. An intermediate is not included in the overall balanced chemical equation. So if you look closely at one of the products in step 1, you will see that NO3 appears as a product in step 1, and then NO3 appears as a reactant in step 2. So NO3 would be classified as an intermediate because it is formed as a product in step 1 and then consumed as a reactant in step 2, and it does not appear in the overall balanced chemical equation. Question 2. A reaction mechanism is shown below that consists of 2 elementary steps. Part A, write the rate law for elementary step number 1. There is only one reactant molecule of O3 in step number 1, so therefore this elementary step is first order with respect to O3. So rate equals K times the concentration of O3, and that's it. Part B, write the rate law for elementary step number 2. Well, in step number 2, we have one molecule of O3 colliding with one particle of O, atomic oxygen. Therefore, this elementary step is first order with respect to O3 and first order with respect to atomic oxygen O. So rate equals K times concentration of O3 times concentration of O. Now, just a quick note about what I've done with the rate constants. Normally, the rate constant is simply written as lowercase k. You don't have to put a subscript 1 or a subscript 2, but the reason I did that was just to remind you that even though we call that a rate constant, it actually doesn't have the same value every single time. The rate constant is very specific to a particular reaction at a particular temperature, so I was just using subscript 1 and subscript 2 to remind you that the value of the rate constant is a very specific value for a particular reaction. All right. We learned that an intermediate is something that is formed in an earlier step and then consumed in a later step. So part C, which substance is classified as an intermediate in this mechanism? So the fact that atomic oxygen, O, is formed in step 1 and then is also consumed in step 2, that makes O, atomic oxygen, the intermediate in this mechanism. And then finally, in part D, write the balanced equation for the overall chemical reaction. Well, on the left, I see 2 molecules of O3, And on the right, I see 3 molecules of O2. So when we add step 1 and step 2 together, this is what we get. 2 molecules of O3 react to produce 3 molecules of O2. That's the overall equation for this reaction. All right, let's move on to number 3. Now we have a different reaction mechanism. So again, we have 2 elementary steps. The rate law for step 1, because I see 1 particle of Cl colliding with 1 molecule of O3, then the rate law would be first order with respect to Cl and first order with respect to O3. And for elementary step number 2, I see 1 particle of ClO colliding with 1 molecule of O3. So again, first order with respect to each of those chemicals, ClO and O3. Again, an intermediate is something that is formed in an earlier step and then later consumed. So I see that ClO is formed in step 1, and then ClO is consumed in step 2. So that makes the particle ClO an intermediate. Now, something we haven't talked about yet so far in this video is a catalyst. A catalyst is not the same as an intermediate. Recall that an intermediate is formed in an earlier step and then consumed in a later step. A catalyst is sort of the reverse of that process. So what a catalyst is a substance that is consumed as a reactant at the very beginning of the mechanism, so in step 1, and then eventually it is also formed as a product in a later step. So a catalyst, like an intermediate, is not included in the overall balanced chemical equation, but where will you see a catalyst? You'll see it as a reactant in step 1, and then eventually you will see it as a product in one of the later steps. So the particle Cl in this particular mechanism is a catalyst. It was added at the beginning, and then it was produced at the end. In part E of this question, it says to write the balanced equation for the overall chemical reaction. So when we add step 1 and step 2 together, I see 2 molecules of O3 on the left, and I see 3 molecules of O2 on the right. So that is the equation for the overall chemical reaction. Now, if you're having a little bit of deja vu from question 2 and question 3, that was intentional on my part. So take a look on this slide. You can see that in question 2 of the packet, the overall equation was 2O3 is turned into 3O2. And in question 3 of this packet, it was the exact same overall equation. So we have 2 different reaction mechanisms, but the same overall equation. So here's the question. Which of the following gives you more details about the process of reactants changing into products? The reaction mechanism, which is a step-by-step process of explaining how bonds are broken and how bonds are formed and what particles are colliding with what particles, or simply looking at the overall equation for the reaction. So hopefully you can see that a reaction mechanism does give us more details, more information about the process of reactants changing into products. All right, our next question in the packet is question 4. The decomposition of NO2Cl occurs according to the equation shown above. A student has proposed the following 2-step mechanism for this reaction. So the first thing I'm going to try to do with this 2-step mechanism is see if I can cross anything off that appears on both the left and the right side of the equation. So I see the particle Cl that is formed as a product in step 1, and then I see that Cl is consumed as a reactant in step 2. So it looks like Cl is potentially an intermediate. Now I'm going to go ahead and see if I can add these 2 steps together. So I see 2 molecules of NO2Cl on the left. I see 1 molecule of NO2, 1 molecule of NOCl, and 1 molecule of ClO. Part A, identify a specific error that causes the student's mechanism to be incorrect. So in the essential knowledge statements for topic 5.7, it says that the elementary steps, when combined, should align with the overall balanced equation of a chemical reaction. So clearly, that's the problem with this mechanism, that when the two steps of the student's proposed mechanism are added together, the overall equation for the reaction does not produce the equation shown above. So in part B, without making any changes to step 1, correct the error described in part A by writing new chemical formulas for the products of step 2 of this mechanism. So the first thing I'm going to do is erase the products which are incorrect, and I'm going to put in that red box in the middle of the slide the correct products that I'm looking for, which are 2 molecules of NO2 and 1 molecule of CO2. So that is what I'm looking for when I add these two steps of the mechanism together. So I already have 1 molecule of NO2 in step 1 as a product. I'd like another molecule of NO2 to be produced in step 2. And I need there to be a molecule of Cl2 produced. So these are the correct products of step 2. It should be NO2 and Cl2. Now, when I add step 1 and step 2 together, I will exactly get the overall balanced equation for the reaction that we started with. Now let's take a look at our next topic. This is topic 5.5, collision model. Here are some essential knowledge statements from the AP Chemistry course and exam description. For an elementary reaction to successfully produce products, reactants must successfully collide to initiate bond-breaking and bond-making events. In most reactions, only a small fraction of the collisions leads to a reaction. Successful collisions have both sufficient energy to overcome the activation energy requirements and orientations that allow the bonds to rearrange in the required manner. The Maxwell Boltzmann distribution curve describes the distribution of particle energies. This distribution can be used to gain a qualitative estimate of the fraction of collisions with sufficient energy to lead to a reaction, and also how that fraction depends on temperature. In topic 5.1, you learned that the rate of a reaction is influenced by changes in reactant concentrations, temperature, and surface area. Changing these variables affects the frequency of collisions between reactant particles. The reactant particles must undergo successful collisions in order for the products to be formed in a chemical reaction. When two reactant particles collide with each other, there are two properties of the collision that will help to determine if the collision is successful, that is, result in the formation of products. The collision must occur with a sufficient amount of energy that is required to overcome the activation energy barrier. And more information on the activation energy of a reaction will be presented in topic 5.6. And when reactant particles collide, they must have the proper orientation or alignment so that certain chemical bonds can be formed and or broken. So here is question 5 in your packet. The graph below shows a distribution for the collision energies of reactant molecules for a chemical reaction at a certain temperature. The dashed vertical line represents the activation energy, which is the minimum amount of energy that is required for the reactants to be converted into products. Part A says on the diagram above, color or shade in the region or area that represents the fraction of collisions that have enough energy to overcome the activation energy barrier. So that would be the portion of the diagram that is located to the right of the activation energy. So if kinetic energy is on the x-axis, then we're only going to shade in that region under the curve that's located to the right of the dashed line. So what does this represent? Well, there's lots of collisions happening in a chemical reaction, but not all of the collisions are actually successful or leading to the formation of products. So at this temperature, only a small fraction of the collisions between the reactant particles have enough energy to overcome the activation energy barrier and then lead to the formation of the products. So Let's think about temperature for a moment. Here is our Maxwell Boltzmann distribution curve for the collision energies of the reactant molecules at a certain temperature. If we increase the temperature, how will the appearance of this Maxwell Boltzmann distribution curve be affected? What I will do is I will put the link to these two Desmos activities or these Desmos graphs in the video description area. So on the left, you can see that there is a Maxwell Boltzmann distribution which is showing an increase in temperature and how that curve is becoming more broad and more flat and how the peak of the curve is shifting toward the right. And we talked about that back in Unit 3, talking about kinetic molecular theory and the properties of gases. But take a look at the activity on the right side of the slide. That's going to be activation energies. You can see that there's a shaded region. That shaded region represents the fraction of reactant particles or collisions that have enough energy to overcome the activation energy barrier. So, as the temperature of the sample of reactant particles increases, the average kinetic energy of the particles increases, and the Maxwell-Boltzmann distribution curve becomes broader and flatter, and as a result of this change, a greater fraction of the collisions between reactant particles will have enough energy to overcome the activation energy barrier. Well, hopefully that part was helpful in terms of that visual. Let's take a look at part B of this question. Does the diagram above represent a sample of reactant molecules at a lower temperature or a higher temperature than the sample represented by the diagram in part A? Justify your answer. So here's what the diagram looked like in part A. You can do a nice comparison of these two diagrams on this slide. Hopefully you can see, based on what I showed you on the previous slide, that the diagram at the bottom here, the one for part B, represents a sample of reactant molecules at a higher temperature than the sample represented by the diagram in part A. So how can we tell? Well, the appearance of the curve is broader and flatter, and the location of the peak of the curve has shifted toward the right, indicating a higher average kinetic energy, therefore a higher temperature. Part C, explain how a higher temperature affects the collisions between reactant particles so that a chemical reaction occurs at a faster rate at a higher temperature. Let's go ahead and shade in that area under the curve for the lower temperature and the higher temperatures. This is a good visual that at a higher temperature, hopefully you can see pretty clearly from the way I've shaded that area to the right of the vertical dashed line, the activation energy, that a higher temperature results in a higher average kinetic energy for the reactant particles. And as a result of this change, a greater fraction of the collisions between reactant particles have enough energy to overcome the activation energy barrier. So in addition to the energy of the collisions between the reactant particles, another factor that will determine whether or not the collision is successful and leads to the formation of products is the orientation of the particles in three-dimensional space, so that when they collide with each other, will they be oriented properly so that a bond can be broken or a bond can be formed? That's what we're going to take a look at in question 6 of this packet. Question 6 says a chemical reaction takes place between NOCl and Cl, according to the equation shown above on the left. Diagrams that represent the reactant particles are shown above on the right. So part A is asking what bond is broken, and part B is asking what bond is formed. So I can tell in the balanced equation that I start with NOCl and then I end with NO. Now, if I didn't have the particle diagrams on the right side of this slide, I might actually get this wrong. I might assume that there is a bond broken between oxygen and chlorine, but in fact, if I look closely at the particle diagram, chlorine is bonded to nitrogen, which is bonded to oxygen. So nitrogen is actually the central atom in this NOCl molecule. So looking closely at this NOCl molecule, if I'd like to form a molecule of nitrogen monoxide, I would like to break the bond in this molecule between chlorine and nitrogen. So right there. So for part A, during this reaction, a bond is broken between chlorine and nitrogen. Now, a product of this reaction is the molecule Cl2. So the particle of Cl is going to collide with the Cl in the molecule, forming a new bond. So I can make Cl2. There is a new bond forming between two atoms of chlorine. Now, in part C of this question, we've already determined in part A and B which bond is broken and which bond is formed. Part C gives us 4 different diagrams that represent collisions or potential collisions between reactant particles. Select the diagram that shows the orientation or the alignment of the particles that is most likely to result in the formation of the products of this reaction. So some of these collisions are not going to be successful, and the particles will just bounce off each other. Even if they have the proper energy, they don't have the proper orientation or alignment. Since I would like a bond to be formed between two atoms of chlorine, the diagram that shows the best orientation or alignment would be this particular diagram, because the particle of chlorine would collide with the chlorine atom in the NOCl molecule, and then that bond would form, causing the bond between the chlorine and the nitrogen to break, again leading to a successful formation of products. But all the other 3 collisions do not have the proper alignment. Now, let's take a look at our next topic. This is topic 5.6, reaction energy profile. Here are some essential knowledge statements from the AP Chemistry course and exam description. Elementary reactions typically involve the breaking of some bonds and the forming of new ones. The reaction coordinate is the axis along which the complex set of motions involved in rearranging reactants to form products can be plotted. The energy profile gives the energy along the reaction coordinate, which typically proceeds from reactants through a transition state to products. The energy difference between the reactants and the transition state is the activation energy for the forward reaction. The rate of an elementary reaction is temperature dependent because the proportion of particle collisions that are energetic enough to reach the transition state varies with temperature. The Arrhenius equation relates the temperature dependence of the rate of an elementary reaction to the activation energy needed by molecular collisions to reach the transition state. And I just wanted to mention to you that additional information related to topic 5.6 will be provided in Unit 6. Unit 6 is entitled Thermochemistry, and topic 6.1, endothermic and exothermic processes, and topic 6.2, energy diagrams, are closely related to topic 5.6, reaction energy profile. Now let's take a look at question 7 in your packet. Question 7 says the following. The diagram shown above on the left represents a reaction energy profile for a chemical reaction. The diagram shown above on the right represents an incomplete reaction energy profile for a different chemical reaction. So on the diagram shown above on the left, we have 3 things to do. First, write an R to indicate the potential energy of the reactants. So we're going to start with reactants. That's going to be the position there on the far left of the diagram. And then we have to put a P on the diagram to indicate the potential energy of the products. So at the end of the chemical reaction, here on the diagram is the location of the products. Now you can see that it's kind of like you're climbing a hill or you're traveling over a hill. That is the location of the transition state at the top of the hill. So it says draw a star to indicate the location of the transition state along the reaction coordinate pathway. And the difference in energy between the reactants and the top there of that hill where the transition state is located, that is the activation energy. So it says draw a vertical arrow to indicate the magnitude of the activation energy barrier for the reaction. So hopefully reactants, products, transition state, activation energy, that all makes sense in this diagram. Now let's move on to part B. Does the diagram shown on the previous page on the left represent the energy profile of a chemical reaction that is classified as endothermic or exothermic? Justify your answer. So you might not know whether this is an endothermic or an exothermic reaction, but here's how you can figure it out. Compare the relative energy of the reactants and the products. So in this example, this represents an exothermic reaction because the potential energy of the products is lower than the potential energy of the reactants. So this indicates that as the reaction proceeds, energy is released. So releasing energy, exothermic, products are at a lower energy level than the reactants. So now we come to the next part of the question. This is part C. Well, if you answered exothermic in part B, which we did, complete the energy diagram shown on the previous page on the right so that it represents the energy profile for an endothermic chemical reaction. So now we want to show that after climbing over that hill, after proceeding through a transition state, now we'd like to finish at a certain level where the products are located. They should be not lower than the reactants, but rather higher than the reactants. So this diagram on the right represents the energy profile of an endothermic reaction because the potential energy of the products is higher than the energy of the reactants. This indicates that energy is absorbed as the reaction proceeds. So when you finish at a level for the products that is lower than where you started for the reactants, it's exothermic. And if you finish at an energy level of the products that's higher than where you started for the reactants, that would be endothermic. All right, this is question 8 of your packet. In question 8, we are given two diagrams, diagram 1 on the left, diagram 2 on the right. Now, since we just talked about endothermic and exothermic reactions, I can just say that both of these energy diagrams represent exothermic reactions. How can we tell? Well, the energy of the products is less than the energy of the reactants. Now, in question 8, you don't have to classify these as endothermic or exothermic. I just wanted to mention that as a point. So what is the difference between diagram 1 and diagram 2? Well, it says that the major difference between them is the relative magnitude of the activation energy. Assuming constant temperature, which diagram, 1 or 2, represents a reaction that should occur at a faster rate? Justify your answer. Now, what I'm going to do is label the activation energy on diagram 1. I would start at the level of the reactants, and I would go all the way up to the top of the hill, as in the transition state. So that right there is the magnitude of the activation energy for diagram 1. And I'll do the same thing for diagram 2. Start with the difference between the energy level of the reactants and the top of the hill where the transition state is located. Hopefully you can tell with this visual comparison side by side that the activation energy for diagram 2 is greater than the activation energy for diagram 1. And if you're not sure how would this difference affect the rate, let me go ahead and talk about it, and I'll show you that Desmos curve, and hopefully that will help you understand it. So here is the difference between diagram 1 and diagram 2. Diagram 2 shows a higher magnitude for the activation energy. Now, this is associated with a slower reaction rate. So I can flip that and say that for diagram 1, because there is a lower magnitude for the activation energy, that would be associated with a faster reaction rate. So again, the official answer for question 8 is the following. Which one would occur at a faster rate? Diagram 1 would represent a reaction that should occur at a faster rate. Why? Because it has a smaller magnitude for the activation energy. Now let's take a look at that Desmos curve. Now what I'm doing here with this Desmos curve is I'm not going to change the temperature. I am not going to change the temperature. What I am going to change is the magnitude of the activation energy. So take a look. You'll notice that what's happening here in this curve is that that vertical dashed line is moving from right to left. So the activation energy barrier is decreasing as that vertical dashed line moves from right to left. But the appearance of the Maxwell Boltzmann distribution curve is not changing at all. So again here, we are not changing the temperature. We're not giving a greater average kinetic energy to these particles. The temperature is staying constant. But what is changing is I'm showing you what happens when the activation energy is decreasing. So on this slide, it says the following. Notice what happens as the activation energy decreases at a given temperature. The result is that, as you can see how that area, that shaded area under the curve is changing, that there is a greater fraction of collisions between reactant particles that have enough energy to overcome the activation energy barrier. And that would result in a faster reaction rate. So we're not changing the temperature, we're simply lowering the activation energy barrier, providing the particles with a greater likelihood that their collisions will be successful and lead to products. All right, so again, to remind you that for the answer for question 8, the diagram on the left, diagram 1, would represent a reaction that should occur at a faster rate because it has a smaller magnitude for its activation energy. Now, before we get to question 9 in the packet, take a look at the essential knowledge statement for topic 5.6 that I have highlighted on this slide. It says, the rate of an elementary reaction is temperature dependent because the proportion of particle collisions that are energetic enough to reach the transition state varies with temperature. And the Arrhenius equation relates the temperature dependence of the rate of an elementary reaction to the activation energy needed by molecular collisions to reach the transition state. So I'd like to spend a few moments focusing on the Arrhenius equation. I know that at the bottom of this slide, and you can see this in your packet, it gives you the following sort of guideline or warning. It says the Arrhenius equation is not included on the AP Chemistry equations and constants sheet, and you will not be asked to do any calculations with the Arrhenius equation on the AP exam. So if you're wondering, why am I talking about it? Well, I think it can be helpful to examine the variables in the Arrhenius equation to recognize the relationships between variables such as the rate constant K, the activation energy, which we label as E sub A, and the overall reaction rate. So here is the relationship between the magnitude of the activation energy and the rate constant K. So in order to begin my little exploration here using the Arrhenius equation and to explore this relationship between the magnitude of the activation energy and the rate constant, I'm just going to make up some values so I can get started. So here is the Arrhenius equation, and I'm going to just make up some values. So the frequency factor is 100. I just made that up. The ideal gas constant, I didn't make that up. That's the actual value, 8.314, and you can see that it says times 10 to the negative 3 after that because I'm converting from joules to kilojoules. Now, 300 Kelvin, I just made that up, and the activation energy is 20 kilojoules per mole. I just made that up. Now, watch what happens to the magnitude of the rate constant when we change the activation energy. So right now, the value for the rate constant that I got on my calculator when I plugged in these values was 0.033. I'm now going to change the activation energy from 20 kilojoules per mole to 25 kilojoules per mole, so I get a new value of K. 30 kilojoules per mole, I get a new value of K. And then 35 kilojoules per mole. So I'm doing this math on the calculator just to show you the relationship between the magnitude of the activation energy and the rate constant. Let me go ahead and start over again. So I did have 0.033 for my rate constant. Now it's getting smaller and smaller and smaller as the magnitude of the activation energy is getting larger and larger. So let's go ahead and summarize this relationship. As the magnitude of the activation energy increases, the magnitude of K, the rate constant, decreases. This makes sense because a higher activation energy should result in a slower reaction rate or a smaller value of K. If I flip it around, as the magnitude of the activation energy decreases, the magnitude of the rate constant increases. This makes sense because a lower activation energy should result in a faster reaction rate or a larger value of K. So now let's go ahead and answer the first part of question 9 on your packet. Question 9. Circle the correct words to complete the following sentences. A relatively small rate constant is associated with a relatively slow reaction rate. A relatively large rate constant is associated with a relatively fast reaction rate. Now let's talk about activation energy. Small activation energy would be associated with a fast reaction rate. Large activation energy would be associated with a slow reaction rate. The next thing I'd like to explore in the Arrhenius equation is the relationship between temperature and the rate constant K. So I'm going to use that same process that I did before. I'm going to go ahead and plug in some numbers into the Arrhenius equation just so I can get started. And so now what I'm going to do is change the temperature and see what happens. So right now the temperature is 300 Kelvin. I'm going to change the temperature from 300 to 350 Kelvin, 400 Kelvin, 450 Kelvin. And when I do that, watch how the magnitude of the rate constant changes. So here it's 300 Kelvin, it's 0.033 for the rate constant. Now this is 350 Kelvin. Rate constant is increasing in value. Here is 400 Kelvin. The rate constant gets higher. Here's 450 Kelvin. It gets higher still. So let's go ahead and summarize. As the temperature increases, the magnitude of the rate constant also increases. Well, this makes sense because a higher temperature should result in a faster reaction rate. If we say it the other way around, as the temperature decreases, the magnitude of the rate constant also decreases. Well, this makes sense because a lower temperature should result in a slower reaction rate. Let's go ahead and finish circling the words in question 9. Increasing the temperature at which a reaction is carried out should increase the reaction rate as well as increase the magnitude of the rate constant. Again, flipping it around, decreasing the temperature at which a reaction is carried out should decrease the reaction rate and also decrease the magnitude of the rate constant. Now, it's very important to know that if you change the temperature at which a reaction is carried out, this will not, repeat, will not change the magnitude of the activation energy. So don't think that because you run the reaction at a higher temperature that you are lowering or changing in any way the activation energy. How you can affect the activation energy is going to be with the use of a catalyst, and we'll talk about that in topic 5.11, but just changing the temperature at which a reaction is carried out will not change the magnitude of the activation energy for the reaction. All right, let's move on to our next topic. This is topic 5.8, reaction mechanism and rate law. Here is one essential knowledge statement for the AP Chemistry course and exam description. For reaction mechanisms in which each elementary step is irreversible or in which the first step is rate limiting, the rate law of the reaction is set by the molecularity of the slowest elementary step, that is, the rate limiting step. So here we have question 10 from your packet. Question 10 says the following. The diagram shown above represents a reaction energy profile for a chemical reaction. Answer the following questions based on the information in the diagram. Part A. Is it more likely that this reaction occurs in a single step or in a two-step process? Justify your answer by referring to specific information from the energy profile. Before I answer this question, let me do a little compare and contrast with question 7 of the packet. So this was the diagram for question 7. And if you recall, we had to put a star to indicate the location of the transition state along the reaction coordinate pathway, and we had to draw a vertical arrow to indicate the magnitude of the activation energy barrier for the reaction. So analyzing this diagram from question 7, hopefully you would agree with the following, that it has one transition state, one activation energy, and would correspond to a one-step process. Now let's compare that with question 10. Here we have two transition states, because there's the first one, there's the second one. Again, the top of the hill is the transition state on the diagram, so we have two of those. We have two activation energies. Let me be careful with how I'm measuring. The activation energy goes from the reactants to the top of the hill, but now in that next step in the process, the activation energy goes from the location of that valley to the top of the hill. So you don't start all the way from the reactants when you're doing that second activation energy. You start from where you began that journey, which is like the valley before that second hill. So those two transition states and two activation energies would imply a two-step process. So the answer to part A is the following. It is likely that this reaction occurs in a two-step process. Why? Because there are two transition states and two activation energies. All right, here's the next part of question 10. If you answered two-step process in part B, which we did, draw a circle or place a circle on the energy profile to indicate the location of an intermediate that is formed along the reaction coordinate pathway. Now, you've heard that word intermediate before. An intermediate from a reaction mechanism is a substance that is formed in an earlier step in the mechanism and then is also consumed in a later step in the mechanism. So at that particular spot where I've labeled it with a little dot there, a little circle on the energy diagram, that would be a substance that is formed in step 1 and then is eventually consumed in step 2. All right, part C. If you answered two-step process for part A, which we did, select one of the following that is more likely to be true for this reaction. Is the first step slower and the second step faster, or is it the other way around? Is the first step faster and the second step slower? Well, how are we going to figure this out? Let's compare the magnitude of the activation energies for step 1 and step 2. So I can see a much larger magnitude of activation energy for step 1 as compared to step 2. And as you recall from earlier in this video, the higher the activation energy is, the slower the reaction rate should be, and then vice versa. The lower the activation energy, the faster the reaction rate. So therefore, based on the appearance of this diagram, because we have a large activation energy in step 1 and a small activation energy in step 2, the first step is a slower step and the second step is a faster step. So it says justify your choice in part C. The activation energy of step 1 is greater than the activation energy of step 2. All right, on the AP exam, the steps of a proposed reaction mechanism are usually labeled as either slow or fast. And the way it works is that only one step of the mechanism will be labeled as slow. So this slow step in the mechanism is known as the rate limiting step or the rate determining step. This elementary step of the mechanism is the one step that will limit or determine the overall reaction rate. Now, in order for a proposed reaction mechanism to be considered plausible or valid, the rate law that is derived from the mechanism must be consistent with the rate law that has been determined from the analysis of experimental data for the reaction. So what we're going to see in this part of the video as we take a look at questions 11, 12, and 13 in your packet is that we have these mechanisms in which one of the steps is labeled as slow and then another step is labeled as fast, and not only are we going to add the steps together to get the equation for the overall reaction, but we're going to have to focus our attention on that slow step, that rate determining step. That's how we can figure out the rate law for the reaction, by focusing on that slow step. So here we go. This is question 11. We have a two-step mechanism, and part A says write the balanced chemical equation for the overall reaction. Now, as I add step 1 and step 2 together, let's see if there's any chemical species that I can cross off because it appears on both sides of the equation. So I see NO₃, which appears as a product in step 1 and also appears as a reactant in step 2. That actually would be an intermediate. Remember, intermediates are formed in an earlier step and then consumed in a later step. The other chemical that I see that can appear on both sides of the equation, so I'm going to get rid of it, would be NO₂, appears on both the left in step 1 and on the right in step 2. Now, you might be thinking, based on that information, that NO₂ would behave as a catalyst. That's actually not correct. It turns out that the reason why NO₂ is not a catalyst, even though I've crossed off a chemical on the left and the right, is because a catalyst should not appear at all in the overall balanced chemical equation. So watch what happens when we add steps 1 and step 2 together. Notice that I crossed off just one of the NO₂ molecules that was present as a reactant in step 1. So if NO₂ were in fact a catalyst, it would not appear at all in the overall balanced chemical equation. So I was just simplifying one of the molecules of NO₂, but NO₂ is not a catalyst because it is in fact a reactant. So the overall balanced chemical equation is NO₂ plus CO to produce NO and CO2. Now, moving on to part B, let's focus our attention on that slow rate determining step. So since step 1 is the slow step, this means that we're going to focus our attention on the reactants in step 1. Here's a little deja vu for you, because earlier in the packet, like at the very beginning, question 1, we had this same mechanism. Although at the time I was not labeling the steps as slow or fast, take a look. That when you have an elementary step, what you do is you count the number of molecules of each chemical, and then that becomes the order with respect to that chemical in the rate law. So we already determined earlier that the rate law for this step would be second order with respect to NO₂, because there are two reactant molecules of NO₂ colliding with each other in this elementary step. So the answer to number 11, part B, is that the rate law would be rate equals K times the concentration of NO₂ raised to the second power. So why is it second order? Because there are two molecules of NO₂ that appear as reactants in this slow rate determining step. All right, moving on to question 12. We have brand new proposed mechanism, and part A is the same as before. We have to write the balanced chemical equation for the overall reaction. Let's see what I can cross off on both sides. So in step 1, I see that atomic oxygen appears as a product, and in step 2, I see that atomic oxygen appears as a reactant. So atomic oxygen would be an intermediate because it's formed in step 1 and then consumed in step 2. I don't see anything else I can cross off on both sides, so I'm going to go ahead and add step 1 and step 2 together, and I see 2 N2O on the left, and on the right I see 2 N2 plus O2. Now, let me focus my attention for part B on the slow rate determining step. So step 1 is the slow step, which means that step 1 is the rate determining step. And what I see in terms of counting the molecules is simply there's only one reactant molecule. There's one reactant molecule of N2O in that slow rate determining step. So my rate law would simply be first order with respect to that chemical. Rate equals K times the concentration of N2O to the first power, and that's it. So before I move on to question 13 of the packet, I just want to make an important point regarding what we saw in questions 11 and 12. You already know how to write a rate law from an elementary step of a mechanism. Now you're learning that the slow step is in fact the rate determining step. So here's the situation that we've seen in questions 11 and 12. If the first step of a mechanism happens to be the slow step, that slow rate determining step, then the rate law of that particular elementary step will be the same as the rate law for the overall reaction. All right, let's move on to question 13. Now, in question 13, it's a little different than questions 11 and 12 because we have a partial mechanism. We don't have the complete information. So in part B, we're going to have to figure out what the chemical equation is for step 1. It says in number 13, a kinetics experiment is performed to study the reaction represented by the equation shown above. Based on the analysis of the experimental data, it is determined that the reaction is first order with respect to O3 and first order with respect to NO2. So they've done the kinetics experiment and they're just telling us first order for those chemicals. So in part A, to write the rate law, all we have to do is understand what that means in terms of first order. That means it would be rate equals K times the concentration of O3 to the first power times the concentration of NO2 to the first power. So we did not analyze a mechanism, we just simply got the experimental data and went straight to the rate law. Now in part B, it says a two-step mechanism has been proposed for this reaction. The first step of the mechanism is the slow rate determining step, and the second step is a fast step. Write the correct chemical equation for step 1 of this proposed mechanism. So let's focus on the fact that we know it's first order with respect to O3, and it's first order with respect to NO2. So that means that there should be on the reactant side in step 1, because that is the slow rate determining step, there should be one molecule of O3 and one molecule of NO2. So we got that directly from the information from the kinetics experiment. Well, now we're not quite done, but at least we got started for step 1. How we finish off the products in step 1 is going to be, are these two steps, when added together, going to give us the overall equation that is shown above? So the first thing I'm going to focus on is the chemical NO3. You'll notice that NO3 does not appear in the reactant at all. It doesn't appear anywhere in the overall balanced equation. So therefore, it must be an intermediate. If it's consumed in step 2, but doesn't appear in the overall equation, then NO3 must have been formed in step 1 and then consumed in step 2. Now we're almost done with step 1. There's one more thing we have to do. We have to recognize that if O2 is one of the products in the overall balanced chemical equation, but it's not appearing anywhere in step 2, then that should show up in step 1 as a product. So if you look at step 1 now, it is complete. And when we add step 1 and step 2 together, crossing off the intermediate NO3 on both sides, then yes, adding steps 1 and step 2 together does in fact give us the overall balanced chemical equation shown above. And because there is one molecule of O3 and one molecule of NO2 as reactants in the slow rate determining step, then this mechanism does in fact agree with the observed rate law from the kinetics experiment. So in order for a proposed reaction mechanism to be considered plausible or valid, the rate law that is derived from the mechanism must be consistent with the rate law that has been determined from the analysis. And we definitely see that the slow step shows one molecule of O3, one molecule of NO2 as reactants. That's why the overall rate law is first order with respect to each of those chemicals. Okay, now let's take a look at our next topic. This is topic 5.9, pre-equilibrium approximation. Here is the essential knowledge statement from the AP Chemistry course and exam description. If the first elementary reaction is not rate limiting, approximations such as pre-equilibrium must be made to determine a rate law expression. So what I'd like to do is contrast what you have already seen in questions 11, 12, and 13 with something different that you're about to see in question 14 of this packet. So if you recall, in questions 11, 12, and 13, the rate law for the overall reaction was based on elementary step 1 of the proposed mechanism. And the reason why it was based on step 1 is because step 1 was identified as the slow rate determining step. So as we're about to see in question 14, in topic 5.9, you will see how the process of writing a rate law for a proposed mechanism becomes more complicated when step 2 of the mechanism is identified as the slow step. All right, let's take a look at question 14. A kinetics experiment is performed to study the reaction represented by the equation shown above. Part A. Is it likely that this reaction occurs in a single elementary step? Justify your answer. So if this were a single elementary step, that would mean that two molecules of nitrogen monoxide, or NO, would have to collide with one molecule of bromine, or Br2, in a single collision. And as I had mentioned earlier in this video, under topic 5.4, elementary reactions involving the simultaneous collision of 3 or more particles are rare. So the answer to number 14, part A, is that it is unlikely that this reaction occurs in a single elementary step, because it would involve the simultaneous collision of 3 reactant molecules. And that would be a very rare event considering the random motion of the reactant particles. So for 3 molecules to collide at one time would be unlikely to occur. Part B. Based on the analysis of experimental data, it is determined that this reaction is second order with respect to NO and first order with respect to Br2. So we're getting that from the analysis of experimental data. So to write the rate law, it would be rate equals K times the concentration of NO raised to the second power because it's second order, and then times the concentration of Br2 raised to the first power. Now, we didn't get those orders from the coefficients in the overall chemical equation. We got it from the analysis of experimental data. So second order with respect to NO, first order with respect to Br2. Now, the following represents a proposed mechanism for this reaction. So we have step 1 and step 2. The steps of this mechanism have not been identified as slow or fast. So in part C, we have to answer the following question. Is it likely that step 1 of this mechanism could be identified as the slow rate determining step? Justify your answer in terms of the rate law written in part B. So in part B, we already have an experimentally determined rate law, which says that it's second order with respect to NO and first order with respect to Br2. And when you're analyzing a mechanism, in order for the proposed reaction mechanism to be considered plausible or valid, the rate law that is derived from the mechanism must be consistent with the rate law that has been determined from the analysis of experimental data for the reaction. So it's not going to be possible to get second order with respect to NO if we only focus on step 1. So if step 1, which has only one molecule of NO as a reactant, If step 1 were the slow rate determining step in this mechanism, then the rate law would have to be first order with respect to NO. Again, because there's only one molecule of NO featured as a reactant. And so first order with respect to NO would not be consistent with the rate law that has already been written in Part B. So the answer to Part C is that it is not likely that step 1 could be identified as the slow rate determining step in the mechanism because it would show first order with respect to NO, and that's not consistent with the rate law in Part B. So what does that mean now? If step 1 is not the slow step, it means that step 2 is going to be the slow step. And we haven't seen this before in the packet. So what do we do if step 2 of the mechanism is the slow step? Let's take a look. In the proposed mechanism shown above, the second step is identified as the slow rate determining step. So the rate law for elementary step number 2 is written as follows. Rate equals K2, and I'm just using a subscript 2 to indicate that particular rate constant for step 2, times the concentration of NOBr2 times the concentration of NO. So it's first order with respect to each chemical because there's exactly one molecule of NOBr2 and one molecule of NO featured as reactants in step 2. So now that we have a rate law, we have a problem. And the problem is that the substance NOBr2 is classified as an intermediate in this mechanism because it is formed in step 1 and then consumed in step 2. Now, in a rate law, you have to know the initial concentration of all of the chemicals that are featured in the rate law. And so because the initial concentration of NOBr2 is unknown, NOBr2 or any intermediate for that matter cannot be included in the rate law of an overall reaction. So we have a problem. We have to find a way to get rid of the NOBr2 in this rate law. So you will now see how the intermediate NOBr2 can be replaced in this rate law based on the information for step 1. So in step 1, it says it's a fast equilibrium. So step 1 is identified as a fast reversible step. The reversibility of a chemical reaction is indicated by the double arrow. And the term equilibrium refers to a situation in which the rate of the forward reaction is equal to the rate of the reverse reaction when equilibrium has been achieved. So we know the rate of the forward reaction in step 1 would equal the rate constant, I'm calling that K1, times the concentration of NO, times the concentration of Br2, because there's exactly one molecule of each of those chemicals featured as reactants in step 1. And then how would we write the rate for the reverse reaction? All we have to do is imagine that we're going in the opposite direction. So NOBr2 would be a reactant in the reverse direction. I'm calling that the rate constant, so K-1, times the concentration of NOBr2. That would be the rate law for the reverse reaction in step 1. Well, since these two rates are the same, we can set them equal to each other. And now that we do that, we can go ahead and solve for the concentration of NOBr2 by putting that expression on a side by itself. So concentration of NOBr2 is equal to K1 divided by K-1, and then times the concentration of NO times the concentration of Br2. And why are we doing this? Because now we can substitute for NOBr2 and get rid of it in our rate law. So substituting this relationship for NOBr2, the concentration of NOBr2, into the rate law for the rate determining step, which is step 2, now we can replace the NOBr2 with the expression that we have. It looks a little bit complicated, but all of those K values can be just merged together as a single rate constant K, and we have NO squared, so to the second power, times Br2. So those concentrations are featured in the rate law. And now, is this a good rate law? Yes, absolutely. And why? Because it is consistent with the experimentally determined rate law that was written in Part B. It shows that the reaction is second order with respect to NO and first order with respect to Br2. So it matches. So what we did was to substitute for that intermediate. We got rid of it so it would no longer appear in the rate law, and now everything looks good with that rate law. All right, let's move on to question 15 of the packet. In question 15, there will be another example of a situation where we have a mechanism in which the second step of the mechanism is the slow step. So we'll see that same procedure featured in question 15. Question 15 says the following. At elevated temperatures, nitrogen dioxide, NO2, decomposes according to the equation shown above. The concentration of a sample of NO2 is monitored over time as it decomposes and is recorded on the graph directly below. So we can see in that first graph that the concentration of NO2 is plotted on the y-axis, and we have time in seconds on the x-axis. The two graphs that follow it are derived from the original data. So those other two graphs, the y-axis is changing, so we have 1 over the concentration of NO2, or the reciprocal of concentration, and then we have the natural log of the concentration. So let's take a look and see which one of these graphs is going to jump out at us. Well, we're looking for a linear relationship, so if the reciprocal of the concentration versus time happens to be a linear relationship or a straight line, that tells us it's second order with respect to that chemical. And sure enough, looking at the y-axis, I see that 1 over the concentration versus time does give us that nice straight line, that linear relationship. Now, you might be thinking, but didn't we know that there's a coefficient of 2 on the reactant side of the equation? Isn't that why it's second order? No, you cannot get the order of a reactant from the coefficient in the overall balanced chemical equation. So we had to figure out it was second order by looking at the data and the analysis of the experiment. All right, so part A. What is the order of the reaction with respect to NO2? Justify your answer. The reaction is second order with respect to NO2 because the plot of the reciprocal of the concentration of NO2 versus time is linear. So the rate law would simply be rate equals K times the concentration of NO2 raised to the second power, because we've determined from the experimental data that it's second order. Now we come to part C. And in part C, we have two different mechanisms. Mechanism number 1, mechanism number 2. And we have to consider if each mechanism is going to be consistent with the experimentally determined rate law that was written in part B. So here, this is a good mechanism to start with because it's simple, straightforward, and what makes it simple and straightforward is that the first step is this slow rate determining step. So all we have to do is focus on the reactants in step 1. So the fact that there are 2 molecules of NO2 featured as reactants in step 1, the slow step, that means that this would be second order with respect to NO2. So the answer is yes. Step 1 in this mechanism is the slow rate determining step. There are 2 reactant molecules of NO2 in step 1. Therefore, the rate law for this step and for the overall reaction is rate equals K times the concentration of NO2 squared. And that is consistent with the second order rate law in part B. So mechanism number 1 was very simple and straightforward because step 1 was the slow rate determining step. Now let's take a look at mechanism number 2. So it's a little more complicated because the first step is a fast equilibrium and the second step is the slow rate determining step. So clearly we have to use that procedure that I have shown you already in this video in question 14, that procedure for how to replace an intermediate in the rate law. So before I dive in to this particular part of question 15, let me just remind you what we did earlier. So here's a general strategy for determining the rate law of a reaction when the second step in the mechanism is the slow step. So this is the reaction mechanism that we saw earlier in the video from problem 14. So the first thing you do is you write the rate law for the slow step of the mechanism. In this particular case, it was rate equals K times concentration of NOBr2 times concentration of NO. Then the next step in the process is if the rate law contains a substance that is an intermediate, which in this case it does, you need to replace it. An intermediate cannot appear in the rate law for the overall reaction. So we have to do something to replace the intermediate. And what we're going to do is focus on step 1. So if step 1 of the mechanism is a fast equilibrium, then you can write an expression that looks like this. Rate of the forward reaction is equal to the rate of the reverse reaction. And then once you write that expression, you can rearrange that equation and use it to write an expression that defines the intermediate. So get the concentration of the intermediate on a side by itself, do a little algebra, and then that way you can replace it in the rate law. So once you have an expression for the concentration of the intermediate equals a bunch of other stuff on the other side of the equation, then you can plug that in, substitute, replace the concentration of the intermediate. And once you do that, it's going to look perhaps a little bit messy, a little bit complicated, but once you clean things up, then you will acknowledge that that rate law is going to be consistent with the experimentally determined rate law for the overall reaction. And the most important feature is that now it no longer contains the intermediate. Okay, so let's go ahead and dive back into this part of question 15. So I've already got my step 2 identified as the slow step. Therefore, the rate would equal K. I'm just calling it K2 because it was step 2. So the rate constant times the concentration of N2O4 to the first power because there's only one molecule of N2O4 featured as a reactant in this elementary step. So again, N2O4, as you can see, was formed in step 1 and then consumed in step 2. So this is an intermediate, and therefore we have to get rid of it. It cannot appear in the rate law for the overall reaction. Luckily, we have a fast equilibrium in step 1. Let's go ahead and proceed. The rate of the forward reaction in step 1 would be K times NO2 squared, because there are 2 molecules of NO2. The reverse reaction would be K times the concentration of N2O4. Again, I'm calling it K1 and K minus 1 just to distinguish between the forward rate constant and the reverse rate constant. I'm now going to set them equal to each other. So K times NO2 squared equals K times N2O4. And when I solve for N2O4, I get that expression on a side by itself. I can now take that expression, which no longer contains the intermediate, and substitute for it in that rate law. The rate law was based on step 2. Step 2 had an intermediate as a reactant. We set up an expression based on the equilibrium in step 1, solve for the concentration of N2O4, and now substitute to get rid of it. So at this point, I now have cleaned up that rate constant. I have NO2 squared, and so now I'm happy with the fact that there's no longer the intermediate. It looks good. So the answer to number 15, part C, Roman numeral 2, is the following. Yes, step 2 in this mechanism is the slow rate determining step. The rate law for step 2 is equal to rate equals K times the concentration of N2O4. Because N2O4 is an intermediate, it cannot appear in the rate law of the overall reaction. So we take a look at the fast equilibrium in step 1. We solve for N2O4, substitute into the expression for the rate law for step 2, and when we're all done, we now have a rate law that, yes, is consistent with the second order rate law in part B. So hopefully the steps in that procedure for how to get rid of the intermediate and then finish up with an acceptable rate law that does agree with the experimental conditions, hopefully that procedure makes sense to you. All right, we're now moving on to a new topic. This is topic 5.10, multi-step reaction energy profile. So here we have an essential knowledge statement from the AP Chemistry course and exam description. Knowledge of the energetics of each elementary reaction or elementary step in a mechanism allows for the construction of an energy profile for a multi-step reaction. So this is topic 5.10, but this is very similar and familiar to an earlier topic, topic 5.6, which was entitled Reaction Energy Profile. So in topic 5.10, we're going to revisit some of those concepts about is it endothermic or exothermic, and talk about the activation energy, is it fast or slow. So this is question 16 in your packet. Nitrogen dioxide, NO2, reacts with fluorine, F2, to produce nitrile fluoride, NO2F. A proposed reaction mechanism is shown below that consists of two elementary steps. Part A, write the balanced equation for the overall chemical reaction. So the first thing I'm going to do is look for any chemical species that appear on opposite sides of the equation so I can cross them out. So let's see here. I see that there is an F atomic fluorine on the right. That is a product in step 1. And I see that same atomic fluorine on the left as a reactant in step 2. So it looks like F, or atomic fluorine, is an intermediate in this mechanism. I think that's it. I think everything else is going to show up in the overall balanced chemical equation for the reaction. So we have 2 molecules of NO2 plus a molecule of F2, and it produces 2 molecules of this nitrile fluoride, NO2F. Part B, write the rate law for this reaction based on the rate determining step of the proposed mechanism. Well, after all the work we did in topic 5.9, with the second step being the slow step, I can imagine you really appreciate it when you see a mechanism that has the slow step as step 1. That makes it really straightforward and easy. So all we have to do is recognize that the first step is the slow step, and then we can focus on the fact that there is 1 molecule of NO2 and 1 molecule of F2 as reactants in that slow rate determining step. So rate equals K times concentration of NO2 times concentration of F2. This rate law shows its first order with respect to each of those chemicals. All right, let's get to the energy diagram. This is part C. It is determined that this overall chemical reaction is classified as exothermic. On the incomplete energy diagram below, draw a curve that shows the following 2 details: the relative activation energy values for the 2 elementary steps of the proposed reaction mechanism, and the change in energy for the overall chemical reaction. So the balanced equation for the overall chemical reaction would be 2NO2 plus F2 produces 2NO2F. Now they've already drawn a horizontal line showing the relative energy of the reactants. The relative energy of the products we know is going to either be higher or lower than the reactants based on whether it's endothermic or exothermic. So they tell us that it has been determined that this reaction is exothermic. Now, if it's exothermic, then the products are going to be lower in energy relative to the reactants. So your diagram would look something like this, where the energy profile for an exothermic reaction shows that the products would be at a lower energy level than the reactants. So if it were endothermic, I would have put the products higher than the reactants. But since it's exothermic, I put them lower. Now, we're not done yet, but at least we've taken care of that second bullet, which is the change in energy for the overall chemical reaction. So that's good. But what about the fact that we have to draw a curve indicating something about activation energy? Now, I could draw the curve like this, but this would be incorrect. And the reason why we cannot draw a curve like this is because we already know it's a 2-step mechanism. So a curve like this would indicate that there's 1 transition state, 1 activation energy, and it would proceed in 1 step. So that's incorrect. The problem is, if we're not careful, we might not know exactly how to draw the relative activation energies of these 2 steps. So I have to be careful about this. Let's go ahead and take a look. The first step is slow. The second step is fast. Step 1 should have a higher activation energy barrier than step 2, because step 1 is the slow step. So the higher the activation energy, the slower the reaction rate. So I want a big hill followed by a small hill in my diagram. Let me go ahead and label this. So this is the activation energy of the first step, which is from the energy of the reactants all the way to the top of that hill, the difference between the transition state in the first step and the energy of the reactants. And then here's my activation energy of the second step. So if you're wondering, how do you know where to measure the activation energy for step 2? It's going to be from the location of that valley where the intermediate is to the top of the hill in step 2. So we have a slow step followed by a fast step because we have a large activation energy and then we have a small activation energy. All right, so that is the correct appearance of the diagram. It takes care of the relative activation energies based on the fact that it's slow followed by fast. And we show that the reaction is exothermic overall because the products are at a lower energy relative to the reactants. All right, moving on to our last topic in this video. This is topic 5.11, catalysis. Here are some essential knowledge statements from the AP Chemistry course and exam description. In order for a catalyst to increase the rate of a reaction, the addition of the catalyst must increase the number of effective collisions and/or provide a reaction path with a lower activation energy relative to the original reaction coordinate. In a reaction mechanism containing a catalyst, the net concentration of the catalyst is constant. However, the catalyst will frequently be consumed in the rate-determining step of the reaction, only to be regenerated in a subsequent step in the mechanism. Some catalysts accelerate a reaction by binding to the reactants. The reactants are either oriented more favorably or react with a lower activation energy. And there is often a new reaction intermediate in which the catalyst is bound to the reactants. Many enzymes function in this manner. Some catalysts involve covalent bonding between the catalyst and the reactants. An example is acid-base catalysis, in which a reactant or intermediate either gains or loses a proton. This introduces a new reaction intermediate and new elementary reactions involving that intermediate. In surface catalysis, a reactant or intermediate binds to or forms a covalent bond with the surface. This introduces elementary reactions involving these new bound reaction intermediates. All right, here we see a graph that we've seen before in this packet. The graph shows a distribution for the collision energies of reactant molecules for a chemical reaction at a certain temperature. The dashed vertical line represents the activation energy, which is the minimum amount of energy that is required in order for the reactants to be converted into products. The shaded region represents the fraction of collisions that have enough energy to overcome the activation energy barrier. So let's explore how the shaded area is affected when the activation energy for the reaction is decreased. Again, I'll put that link in the video description area. So take a look at that dashed vertical line as it moves from right to left. So as the activation energy is lowered, you can see a greater shaded area under that curve representing the fraction of the collisions that are successful or have enough energy to overcome the activation energy barrier. So the presence of a catalyst can provide an alternate reaction pathway that has a lower activation energy. If the activation energy decreases, then there should be a greater fraction of collisions between reactant particles that have enough energy to overcome the activation energy barrier, and this results in a faster reaction rate. Here is the uncatalyzed situation with a higher activation energy. Now that dashed vertical line is shifted toward the left, here could be the catalyzed situation with a lower activation energy. Again, a greater fraction of the molecules have the energy needed to overcome the activation energy barrier. So note that when a catalyst is added to the reaction mixture, this does not change the temperature. It does not increase or change in any way the average kinetic energy of the reactant particles. So important information about catalysts. The presence of a catalyst increases the reaction rate by providing an alternate reaction pathway with a lower activation energy. Adding a catalyst to the reaction mixture does not change the temperature at which the reaction is carried out. A catalyst does not change the potential energy values for either the reactants or the products, so that difference in energy between the products and the reactants will remain the same. Question 17. In the energy diagram shown above, which reaction pathway, the solid line or the dashed line, represents a reaction that occurs in the presence of a catalyst? Justify your answer. So the solid reaction pathway has a higher activation energy. The dashed reaction pathway has a lower activation energy. So therefore, the uncatalyzed pathway would be the solid line, and the catalyzed pathway would be the dashed line. Take a look at the energy difference between reactants and products. You can see that the energy difference between reactants and products is the same for either the uncatalyzed or the catalyzed version of this reaction. So adding a catalyst does not change the potential energy of either the reactants or the products. All right, well, that was the last question in the packet. I hope that you found the answers and explanations helpful. Thanks for watching.